Conditional probability example. So first thing, just read through the problem, see what's going on, get your mind wrapped around it a little. So we have seeds from maize ears carry either single spikelets or paired spikelets, but not both. Progeny tests on approximately 600 maize ears revealed the following information. 40% of all seeds carry single spikelets, while 60% carry paired spikelets. A seed with single spikelets will produce maize ears with single spikelets 29% of the time and paired spikelets 71% of the time. And then a seed with paired spikelets will produce maize ears with single spikelets 26% of the time and paired spikelets 74% of the time. And then we want to find the probability that a randomly selected maize ear seed will be one of these three things: carries a single spikelet and produces ears with single spikelets, produces ears with paired spikelets, and then carries a paired spikelet given that it produces ears with paired spikelets. So before I start getting into the answers for 1, 2, and 3, I want to get the information out of the main body of the paragraph written in notation that will actually work for us and start help us getting to the final answer. So I'm just going to go up to the 40%. So I'm going to just use the probability of S for single, and that's going to be 40%, so 0.40. The probability of paired, I would just use that for P, that's going to be 0.60. And then they give you some information. Given that it was single, so it has a single spikelet, it's going to produce a certain spikelet with different percentages. So I'm going to use this notation SP, so it's a single producer, given that it came from a single spikelet, is going to be 29% of the time. That's coming from that sentence right here. And then it'll have a paired one 71% of the time. So it'll be a paired producer, given that it was single, 71% of the time. And then the next sentence gives us information about if it was a paired one to start out and what it produces depending on, if it was paired. So we'll have this probability of being a single producer, given that it was paired, is going to be 0.26. And the probability that it's going to be a paired producer, given that it was paired, is going to be 0.74. And if we look at this in just a little tree diagram here, this will be helpful, especially for parts 2 and 3. What we have here really is some information that it's either going to be single or paired, and then it's going to produce a single or produce a paired, depending on if it's single, and it'll produce a single or produce a paired given on, if it's paired. And what we have here is these probabilities kind of lining up. We got the 0.40 here, we got the 0.60 here on this branch, and then being a single producer, given that it came from the single, we got this 0.29 here. And then the paired producer would be the 0.71. I'll just write that kind of up here. And then we'll have the 0.26 being a single producer from a pair, and the 0.74 being a paired producer from a pair. And just for the sake of consistency, I'll put some zeros in front of those decimals there and there. So now, moving into the actual things we're looking at, all I've done so far is just organize the information. This is really helpful as you start working through these problems sometimes, to just have this information organized. And the first problem they want, it carries a single and it produces ears with single. So if I write this out, it's single and it produces ears with single. It would be the probability of S and that S sub P notation that I'm using. And with the and, this is a dependent situation, so we do have to use the conditional probability. So I'm going to have here just the probability of single, and then times the probability of it's a single producer given that it came from that single group. And we can just multiply these out. So we get the 0.40 here times 0.29. And that ends up equaling our 0.116. So that is a good answer there for that one. Now in the second one, we want the probability of producing ears with paired spikelets. So what I'm looking at for part 2 is the probability of producing pairs. So I want this probability of P sub P for the way that I'm notating things. So when I look at my overall tree diagram, I've got a paired producer here, I've got a paired producer here. And in order to get the full probability, we got to work down the tree. So we just come all the way down here, and we come all the way down here. And that means I'm going to be multiplying the 0.40 times 0.71, and then adding that to the other branch followed through, the 0.60 times the 0.74. So this will give me, just writing it out, we got the probability of being single times the probability of being a paired producer, given that it was single, and then adding that to the probability of being a pair times the probability of being a paired producer, given that it was a pair. And again, these probabilities, we'll just write them out here. We got the 0.40 times the 0.71, and then plus the 0.60 times the 0.74. And I guess I could do that again for consistency. And when you work that out, you get 0.728. So then for the last one, it carries a paired spikelet given that it produces ears with paired spikelets. So let's write this out in notation. This given, that's the conditional, that's a key word for conditional. So whatever comes after that word given is going to be what comes after that vertical bar. And whatever comes before given is going to be what comes before the vertical bar in this notation. So we want it to be the probability of being paired given that it produces pairs. So we want this probability using the notation that I've been using. Now when I look up here at what I've already written, notice I don't have any of that where the given condition was what type of producer it was. We were just told what it was originally, whether it was single or paired originally. So this is a place where we do have to use the Bayes formula. Bayes formula allows you to switch the order on these conditionals if you know enough information. So Bayes formula is just great for these scenarios and it always shows up. So the Bayes formula for this, sometimes Bayes Theorem or whatever, but what we get is, in general, the probability of A given B can be rewritten using his formula here, his theorem, that the probability of B given A times the probability of A, and we divide that by the probability of B. So this works out really great in this case, because if I write this form now using Bayes' formula here, we can get this probability of P producer, given that it was P or paired, times the probability of paired, which I have that information, divided by the probability of being a paired producer, which I figured that out in the second part. So I got all the information I need in order to put this together. And the probability of being a paired producer, given that it was paired, if I just look up here again for this real quick, see that that's at 0.74. So I can just write that down here. The probability of being paired originally was the 0.60. And then the probability of being a paired producer, we found that answer in part 2. That was 0.728. And when you work that all out, you get 0.6, and it's really 0.6098. But if I round the 3 decimal places, the 9 goes up and we just get this 0.610. Okay, so nice conditional probability example. If you do have questions, don't be afraid to put those into the chat. And thank you for watching.